From this point forward in the course, we're going to be looking at sequences and series, which is a first foray into discrete style functions. Now, we spend a lot of time in calculus talking about a continuous function. And the idea of a continuous function is, of course, that the working definition, at least, is that there are no breaks or holes in the graph, no jumps. A common way to describe it is that if we were to graph it, we could graph it without ever having to lift our pencil or pen up off of the page. But what that ultimately means is there are no vertical asymptotes, there are no holes in the graph, there are no jumps, as you would often see in a piecewise defined function. However, in order to make this happen, the function has to be defined at every single individual point in an interval. Every individual point. That means not just at x equals 1 and x equals 2, but also at every point in between them. X equals 1.5, x equals 1.1, x equals 1.956382749. No matter how far you zoom in, so to speak, you will always find the function there. Discrete functions, however, or functions that operate discretely, the difference between discrete and continuous is the level of precision to which we can operate. Continuous functions can operate on an infinite level of precision. No matter what two values you're looking at, you can always find something in between them. All you would need to do is simply add on more decimal places. Discrete functions have a finite level of accuracy, which usually takes the form of a finite number of decimal places that you are allowed to work with. A common example would be money, which is typically measured to 2 decimal places. We can have dollars and then cents. Now, in theory, it could go beyond that, but typically money is only reported or used with 2 decimal places. Now, that being said, sequences are our first look at a discrete function. Mathematically, the definition of a sequence is that it is a function whose domain is only positive integers. In this way, we can't talk about this in terms of a graph the way we typically would. The basic idea of the graph of a continuous function is that we graph a few individual points and then we draw a smooth curve between them. In the case of a sequence, the only inputs are positive integers, not even negative integers, just positive integers. Which means that if we were to plot points, we would only have those points. We would have nothing more than those points. For example, if we were to look at a function, f of x equals, let's keep it simple, f of x is equal to 1/2 x plus 1. For a continuous function, we would represent this by marking the y-intercept, which would be 1, and then we would use the slope to go up 1 and right 2. If we chose to, what we could do is in between them at x equals 1, we could mark a y value of 3 halves. At x equals 2, we'd have a y value of 2. At x equals 3, we'd have a y value of 5 halves. At x equals 4, we'd have a y value of 2. A y value of 3. And so on. The continuous function would then continue in both directions, so that ultimately we would connect these with a line. This would be the continuous function f of x is equal to 1/2 x plus 1. On the other hand, the sequence, the notation for a sequence is typically written in this way. The sequence, if we were to graph that, would consist only of the points, and even then, only of the points that have positive integer input values. Now, very often this will also include 0. So when we say positive integers, it is occasionally, it is done with n equals 0 as well. But even without the n equals 0, we would have a point when n equals 1, a y value of 3 halves. When n equals 2, a y value of 2. When n equals 3, a y value of 5 halves. When n equals 4, a y value of 2, and so on. And unlike a continuous function, we would not connect this with a line. The point is that these dots in the continuous function are some solution points, and by using some solution points, we are able to fill in all the rest of the solution points in between them. We don't do that here because there are no solution points in between these. These are the input and output pairs, and they're all the only input and output pairs. So here we have this connected, we connect the points with a line, or in the case of other styles of functions, it would be a curve, to show all of the solution points between the ones that were plotted. In the case of a sequence, the points are not connected, and the reason being that if the purpose of connecting them was to show solution points between the ones that were plotted, there are no solution points between the ones that are plotted. And that is the fundamental difference between a sequence and a continuous function. Now, this is going to certainly make things a bit more interesting because every single thing that we have done in calculus has been based on having a continuous function. And sequences are, by their very definition, not continuous. So the remainder of this unit is going to be spent in examining these sequences, and as we will see, they turn into, in the next lesson, series, to look at their behavior and to figure out how we're going to make this work given the tools that we have available to us in calculus. Now, the first basic thing of a sequence is the notation. We saw it briefly in the example on the previous slide here, but the notation for a sequence starts with this, that for each value of n, starting at 1, and then 2, and then 3, and so on, the terms are listed as a variable with a subscript, where a sub n is the nth term of the sequence. As such, we usually then would take the formula, as we saw in the previous example, the formula for a function, and rewrite it with the variable n, so that the notation would become a sub n in braces is equal to the formula in terms of n. An alternative to this notation sometimes includes, much like summation notation, an acknowledgement of the initial value of n and the final value of n, which in this case is infinity. An example of this might be something such as this, to list the first 5 terms of the sequence defined by the formula n squared plus 1 over 2 to the n. So when n equals 1, our first term, a sub 1, would be 1 squared plus 1 over 2 to the first, which, as it turns out, is just equal to 1. When n equals 2, a sub 2 would be 2 squared plus 1 over 2 to the second power, which would give us 5/4 in this case. When n is 3, a sub 3 would be 3 squared plus 1 over 2 to the third, which happens to also give us 5/4. In the case of n equals 4, we have 4 squared plus 1 over 2 to the fourth, which would be 17 over 16. And when n equals 5, a sub 5 would be 5 squared plus 1 over 2 to the fifth, which would give us 26 over 32, or 13 over 16. Quite simply, it's much like a function, except we are only allowed to use integer exponents, which actually, I suppose, makes our lives a little bit easier, because if we were to, say, have to graph a function by hand, we'd probably only use the integer inputs anyway. And then we'd have to connect them with a line when we graphed it. Here, we don't have to connect them with anything. All we have to do is list some of the terms of the sequence. Now, in theory, this sequence could go on forever, so are we supposed to list out all of the terms forever? Of course not. One of the big important things about sequences, and the thing that we focus on the most about them, is whether they converge, or conversely, whether they diverge. The idea is that looking at the terms of the sequence, we want to see, do those terms approach a unique finite value? If the terms of a sequence approach the unique finite value L as n goes to infinity, meaning the further out we go into the sequence, if the terms are approaching this unique finite value L, then the sequence converges. Another way to say this is that the limit as n approaches infinity of a sub n is equal to L. If this is not true, if the terms of the sequence do not approach a unique value, or do not approach a finite value, or do not approach a unique and finite value, then the sequence diverges. Some relatively obvious examples of this would be the sequence of just n, which would be when n is 1, the term would be 1. When n is 2, the term would be 2. When n is 3, the term would be 3. When n is 4, the term would be 4. And so on. In this case, the terms continue to grow and grow and grow. So the limit as n approaches infinity of n is, of course, infinity. This sequence diverges. On the other hand, if the formula for the terms of our sequence is 1 over n squared, then the terms of the sequence would be 1 over 1 squared, and then 1 over 2 squared, and then 1 over 3 squared, and then 1 over 4 squared, etc. In this case, the terms are obviously approaching 0. In this case, the sequence 1 over n squared converges. Now, these are obvious examples. Not all of the such sequences are going to be quite so obvious. On the other hand, we can always list out some of the terms, as I did here. One interesting thing that does happen with sequences, because they are discrete, not continuous, we have an interesting thing happen with them that hasn't happened in any continuous function. Suppose our sequence is 3 plus -1 to the n. Now, in a continuous function, we are not allowed to have a negative base for our exponent. The rule for exponential functions was that the base always had to be positive and could not be equal to 1. In this case, our base is negative, which seems like it should not be acceptable, except for the fact that since we are only using positive integer values for n, we can actually work with this. For example, our first term would be 3 plus -1 to the first. Our second term would be 3 plus -1 to the second. And then 3 plus -1 to the third, etc. -1 to the first is -1. So 3 plus -1 gives us 2 for our first term. However, -1 squared is +1. And 3 plus +1 gives us 4 for our second term. Then we have 3 plus -1 to the third power. -1 is 1 raised to a power, which will always give us 1. The only difference here is the negative sign. And as we know from having dealt with powers in the past, any negative number raised to an odd power will result in an odd number, and any negative number raised to an even power will result in a positive number. So we're always going to get either +1 or -1 for that second term, depending on whether the power is even or odd. So when we again have -1 cubed, we will get again -1, just like we did over here. So once again, we will end up with 3 plus -1 is 2. Then we would have 3 plus -1 to the fourth, where -1 to the fourth would give us +1, just as this would give us +1. So what we end up with here is something known as an alternating series, in the sense that it alternates between the two values 2 and 4 forever. In this case, the limit as n approaches infinity does not exist. While all of the terms are finite, and they never grow any larger than 4 or shrink any smaller than 2, the limit does not exist because this does not approach a unique value. So in this case, we would say that the sequence described by the formula 3 plus negative 1 to the n diverges. Now, in some cases, listing out terms may not result in something that's incredibly obvious. For example, earlier, we used the example of the sequence n squared plus 1 over 2 to the n. And the terms of this sequence ended up being 1, and then 5/4, and then 5/4 again, and then 17/16, and then 13/16. Excuse me. And these are not so obvious. We would probably have to go to considerably more terms to be able to get a definitive feel for what this is doing. So the alternative, of course, is to actually evaluate the limit. Rather than use the terms of the sequence, we can actually just do the limit of the expression itself. It's a good thing we talked about how to evaluate limits, particularly in the case of something like this, because if we try to put in an incredibly large value for n, the top will approach infinity, but so will the bottom. And this is when we need L'Hopital's rule. Now remember, L'Hopital's rule only works under certain circumstances. The numerator and denominator both have to approach 0, or both have to be approaching infinity, positives or negatives notwithstanding. So before we can use L'Hopital's rule, we need to verify that this is the case. And we just did. So what we can do now is the derivative of the numerator over the derivative of the denominator. And we can take the limit of those two things. The derivative of n squared plus 1 is, of course, 2n. In the denominator, we have the derivative of 2 to the n, which is 2 to the n times the natural log of 2. Now this, unfortunately, still approaches infinity in both the top and the bottom. So we will have to use L'Hopital's rule a second time. This time, we're doing the derivative of 2n in the numerator, and the denominator, the derivative of 2 to the n times the natural log of 2. Of course, then, the derivative in the top is just going to be 2, and that's good enough to break the indeterminate form, because even when n goes to infinity, the numerator will remain a 2. In the denominator, then, the natural log of 2 is a constant coefficient, so the derivative of 2 to the n is 2 to the n times the natural log of 2, times the natural log of 2 that's already there. Now, again, the natural log of 2 is a constant, so squaring it is also a constant, but 2 to the n in the denominator will continue to go to infinity. However, as we mentioned before, in the top, the 2 in the top will remain a 2. And this is now enough to say that the terms of this sequence do approach 0. Now, looking at the terms of the sequence up here, we can see that the first term is 1, and the next term actually grows. The second term is actually a little bit bigger than the first. And then the third term, instead of growing, it actually stays the same. And then after that, it starts to drop. Now, how do we know this drops? Because this is 1 and 1/4. This would be 1 and 1/16. So it is still bigger than 1, but it is not as much bigger than 1 as the previous term. The next term is even smaller than 1. So while we haven't gone very far out into the sequence, we still can see here that the terms are eventually starting to get smaller. We can only assume without finding more terms that they would continue to get smaller, except for the fact that we just did the algebra to show that the limit does approach 0. So we can therefore conclude that the sequence described by n squared plus 1 over 2 to the n converges. Now, much like limits have certain properties that go with them, because sequences converge or don't converge, diverge, based on limits, properties of limits can extend to sequences as well. So we're going to start with establishing a couple of facts. We're going to suppose that we have a sequence described by A sub n, and we're going to suppose that it converges because it has a unique finite value that the terms approach. And then we're going to have a second sequence that also converges. We'll call this sequence B sub n, and we'll say that it converges as well to some other value, which we will call k. The following properties hold true then. That if the two sequences are convergent, that is to say, if all of the terms of A sub n are approaching something, and all of the terms of B sub n are also approaching something, that to add the terms of those sequences together should also result in a finite sum, a finite result, that happens to be the sum of the two terms of the sequences. And this is easily extended to subtraction, as we know from dealing with properties of limits and derivatives and integrals. When something applies to addition, it very easily is shown to apply to subtraction. So the idea is that if we're taking terms that are finite in value and adding them together, then their sum is finite in value, and therefore it should approach the sum of the sequence, the convergent value of the sequences. Likewise, if every term of a sequence is scaled by a multiple c, then if the terms of the sequence converge, as claimed in our premise up here, if all of those terms of the sequence converge, then simply making them all twice as big or 5 times as big is not going to affect the fact that they still approach a finite value. They just approach a value that is twice as big or 5 times as big. So this does not change the convergence of the sequence. it simply changes the value to which it converges. And this holds for any real number c. What if then, instead of adding or subtracting the terms of the sequences, or instead of multiplying the terms of the sequences by the same value, what if we multiply the corresponding terms of the sequences together? Well, given that what we said for property number 1, that if the terms of the first sequence, a sub n, are all finite and are all approaching something, and the terms of the sequence b sub n are also all finite and approaching something, then adding them together should still result in something finite that is then approaching something. Well, why not for multiplication then? If we multiply two numbers that are finite, we should then again get a finite number. And furthermore, the result of this new sequence should simply be the product of the two individual sequences. And lastly is division. Of course, division does bring with it a new consideration here, that at no point can the terms can any term of the sequence in the denominator be 0. And the sequence in the denominator cannot converge to 0 either. Standard rules for division, that the denominators cannot be 0. There is another property or theorem that follows from this as well, and it is known as the squeeze theorem for sequences. The squeeze theorem for sequences says that if we have two convergent series, or sequences rather, and they both converge to the same value, if there is then a third sequence C sub n, such that the terms of the sequence of C are between the terms of the sequences of A and B once we pass beyond some particular threshold. In that case, then the limit of the new sequence, C, is also L. Now, what on earth does all this say? First of all, let's deal with that big N and the little n. Now, the idea of looking at the limiting value of a sequence is not what it's doing in its first few terms, it's what it's doing far out in the sequence. That's why we look at the limit as n approaches infinity. For example, we had a sequence earlier that actually started by getting a little bit bigger at first before it started getting smaller. And the sequence did converge to 0, but at first it started at 1 and got bigger before shrinking back down. The point is that what happens at the beginning of a sequence is not important in terms of its convergence or divergence. What's important is what the sequence does further on down the line. So this big N is meant to say that at the beginning, this rule may not hold, but at some point, the rule has to take over that the sequence C, every term of the sequence C, has to be between the corresponding terms of the sequences A and B. So eventually, that's what this for n, little n is greater than big N means. At some point, it has to take over that the sequence C is between the sequences A and B. Well, if the terms of A approach a certain value and the terms of B approach that same value, and C is between them, then C gets sandwiched. C ends up getting sandwiched in between them because it has to stay smaller than B, and yet has to stay bigger than A. And if A and B both squeeze together towards the same value, then C is forced to squeeze into that same value as well. Now, the squeeze theorem here is meant to help give us an option for how to show that the terms of a sequence do approach a limiting value when maybe the formula for the sequence is not so easy to deal with. An example would be something that includes a factorial operation. So as a quick little aside here, there is a new operation that we need to introduce that we will see often throughout this, and there's a reason that it has not come up in math previously. Everything that you've done in math prior to this has been about continuous functions. Even all the way back into the beginning of algebra, everything has been continuous. A factorial is a specifically discrete operation. A factorial is denoted with an exclamation point. And the definition of a factorial is that it is the sum of all integers starting from 1 up to the value given. For example, 6 factorial would be equal to 1 times 2 times 3 times 4 times 5 times 6. 8 factorial would be equal to 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. I think you can see the problem here if we attempted to do this in a continuous fashion. It's bad enough when we have 8 factorial having to multiply all of these numbers together, and yes, it gets quite large. However, imagine having to multiply all of the infinite values that are between 1 and 2 as well, and all of the infinite values that are between 2 and 3 as well, and all of the infinite values between... It would get out of hand very quickly. So this is only applicable to discrete... in discrete situations. Furthermore, it lends itself well to sequences, and later on, as we'll see, series, because it only works for positive integer values of n, which was the definition of what a sequence is, that it is a function that's domain is positive integer values. So the factorial is something that hasn't come up before because it was not something that we were able to apply to any of the concepts that we were working with. But it is uniquely suited to sequences, and in later lessons, to series. Now, what that means in terms of the squeeze theorem would be something like this. Suppose our sequence is defined by -1 raised to the n times 1 over n factorial. Now, this would be difficult to show whether it converges just on its own for two reasons. One, we've got this factorial operation, which is not necessarily the easiest thing to work with, being that it's completely brand new. But more than that, we have that -1 to the n, which we saw in a previous example, creates an alternating situation here. In this case, to actually list out the terms of the sequence would make it perhaps a little bit difficult to work with, because when n is 1, we would end up with -1. But when n is 2, we would end up with +1/2. And then when n is 3, we would end up with -1/6. And then +1/24. And then -1/120. And while we can see that the size of the fractions themselves seems to be getting smaller and smaller, that alternating sign where the terms alternate between negative and positive makes it perhaps a little bit tougher to deal with. Now, that being said, what we can do is come up with two series to compare it to. One that has terms that are always larger than it, and the other that has terms that are always smaller than it. Again, maybe not in the first couple of terms, but as long as at some point that rule takes over, then we should be good. Now, the series that we're going to look at are going to be a sub n for our smaller series, -1/2 to the n. And for our larger series, which we will call b sub n, we're going to use +1/2 to the n. The idea here is that we can show that 2 to the n is always smaller than n factorial, and therefore 1/2 to the n is always bigger than 1/n factorial. If we can show that this is true, then it will therefore mean that 1/2 to the n is bigger than 1/n factorial. This by the rules of reciprocation. The bigger a number is, the smaller its reciprocal will be. Well, n factorial is going to be equal to 1 times 2 times 3 times 4 times 5, etc., all the way up to n. 2 to the n, however, is going to be equal to 2 times 2 times 2 times 2 times 2, etc., so that we have n factors of 2. Now, at first, if we only consider the first terms, 2 to the n is bigger. And that's not actually what we want. We want 2 to the n to be smaller. So then let's look at the first two terms of each thing here. 2 factorial is going to be equal to 1 times 2 is 2. 2 to the second power is going to be 4. So once again, 2 squared is bigger. Going out to 3 factorial, 3 factorial is equal to 6. 2 cubed is equal to 8. So once again, 2 to the n is still bigger. It isn't until we reach the fourth term, or the fourth part of this, when n is 4. 1 times 2 times 3 times 4 is 24. Whereas 2 times 2 times 2 times 2 is 16. So that's where the cutoff is. So for n equals 1, 2, and 3, 2 to the n is bigger than n factorial. But the second we get beyond that, 2 to the n is now smaller than n factorial. And that's what we need, is that at some point in the progression, n factorial has to be bigger than 2 to the n. And that is what occurs once we get to the fourth term of the sequences. So this means that the conclusion is that farther out in the sequences, 1 over 2 to the n is bigger than 1 over n factorial. Thus, every term for once we get to 4 or greater, every term in the main sequence is going to be smaller than the terms of the sequence 1 over 2 to the n. This holds even with the negative, even with the alternating things, because if all of the positive terms are less than 1 over 2 to the n, then certainly all the negative terms will also be less than 1 over 2 to the n. On the other hand, all of these terms are also going to be bigger than negative 1 over 2 to the n. The idea is that 1 over 2 to the n is larger in magnitude. If we're comparing the positive terms of our main sequence, then positive terms are always smaller than positive 1 over 2 to the n. If we are looking at the negative terms of the sequence, they are always larger than negative 1 over 2 to the n. So we have neatly placed our main sequence sandwiched or squeezed between these two. The difference is that 1 over 2 to the n, and in turn negative 1 over 2 to the n, are much easier to work with in terms of a limit. As n approaches infinity, 2 to the n will approach infinity. But since the numerator is a constant 1, the terms of this sequence will approach 0. Likewise, the sequence negative 1 over 2 to the n will also approach 0. The negative sign in front does not actually affect this. So therefore, since the limit as n approaches infinity of the smallest of the three sequences and the limit as n approaches infinity of the largest of the three sequences are both 0, then the limit of the sequence that's in the middle must also be 0. And thus we can say that the sequence defined by -1 to the n times 1 over n factorial converges. It is squeezed in between a convergence sequence from above and a convergence sequence from below. Now, the alternating nature of that sequence caused us to have to squeeze this in between two things. But what we saw was that the sequence that bound it from above, 1 over 2 to the n, was the same basic sequence that bound it from below. We just needed a negative sign. So based on that logic, we have another theorem here that says for a sequence, a general sequence, a sub n, if the limit as n approaches infinity of a sub n, of the absolute value of a sub n, equals 0, that means if we remove any alternating signs, if we have terms that are negative, we're just going to ignore the negative signs and look at the magnitude only of the terms. If the magnitude of the terms approaches 0, regardless of positive or negative, then the sequence converges to 0 even with the negatives. What this basically says is that if we are dealing with an alternating sequence, as we saw in the previous example, that we could just ignore the alternating sign of it and only bound it from above with the positive 1 over 2 to the n, and it would suffice. Now, a slightly less common concept in sequences that we may still have to deal with, and we will in the future lesson, is being able to define a formula for the terms of a sequence. That is to say, we might be able to identify the values of the terms of a sequence. So suppose we know a sub 1, a sub 2, a sub 3. Now, 3 is the absolute bare minimum number of things required to establish a pattern. Typically, if we want to be extra sure, we go a little bit further than that. So 3 is the bare minimum number of terms of the sequence that you need. 4 would be better, 5 is even better. this is going to be based on pattern recognition. For example, suppose the first 5 terms of a sequence are 2, or 2 over 1 as we'll write it, and then 4 over 3, and then 8 over 5, and then 16 over 7, and then 32 over 9. Can we define a formula for a sub n? Now, the fact that these are all fractions suggests that we might be able to find a pattern in the numerators completely separate from the pattern of the denominators. And the pattern of the denominators should, I hope, be pretty easy. It's going by odd numbers, so that if we needed to calculate or if we needed to determine the next term of the sequence would probably be something with an 11 in the denominator. And we can base that off of the fact that the denominator they are consecutive odd numbers. The numerators might not be quite as obvious in this case, but they're still not all that hard to notice. They are powers of 2. 2 to the first power, 2 to the second power, 2 to the third power, 2 to the fourth, 2 to the fifth. If this continues, then the next numerator should be 2 to the sixth, or 64. This then should make this pretty easy to establish then. The nth term of the sequence should simply be, in the numerator, the nth power of 2. The denominator might be slightly trickier to define, but the fact that it counts up by 2's, it goes from 1 to 3 to 5 to 7 to 9, and then to 11, that's a linear pattern. It's always going up by the same amount. So it would have to be going up by a slope of 2. Of course, for the first term, 2 times 1 would be 2, not 1. And for the second term, 2 times 2 would be 4, not 3. And then 2 times 3 would be 6, not 5. So we can fix that by subtracting 1 from 2 to the n, or 2 times n. So 2 times n minus 1 would give us the odd numbers that are in the denominators. And this is the nth term of our sequence. There are a couple of other topics that we need to talk about with sequences that will be relevant moving forward. The idea that a sequence can be monotonic and or bounded. Monotonic comes from the root word of monotony. It means that the terms of the sequence are progressing in a pattern that doesn't change. Not the values of them per se, but in this case, we're going to be talking about whether they are increasing or decreasing, or rather, non-increasing or non-decreasing. So a sequence defined by A sub n, is monotonic if 1, its terms are non-decreasing, non-decreasing sounds weird. Why not just say increasing? Well, it's like saying positive and negative. Neither one of them includes 0. So saying something is positive is different than saying it is non-negative. Non-decreasing doesn't mean it has to be increasing, it just means it has to not be getting any smaller. That is to say, whatever the first term is, the next term has to be at least as big as it, if not bigger. And then whatever that term is, the next one has to be at least as big, if not bigger. And the next one has to be at least as big, if not bigger. And that pattern has to continue throughout the entirety of the sequence. So non-decreasing means the terms never get smaller. They might get bigger, they might stay the same, but they don't get smaller. Of course, it could be the other way. Its terms could be non-increasing. Which means that whatever the first term is, the next one would be smaller or the same, but not any bigger. And the next one would be smaller still, or the same, but not bigger. And that's what non-increasing means, is that throughout the entirety of the sequence, each term cannot be any bigger than the ones before it. For example, here's a sequence we saw before. This ended up having terms that went back and forth between 2 and 4 forever. This is not monotonic. The reason being that our first term is 2. Our next term is 4, which is bigger than 2. That establishes this as the terms are getting bigger, or at least not getting any smaller. In order to be monotonic, the terms would have to continue to get bigger, or at least not any smaller. So the next term, after the 4, would have to be bigger than or equal to 4, and it's not. It went back down. And then back up again. And then back down. So this increases from 2 to 4, and then decreases from 4 to 2. And then increases, and then decreases, and then increases, and so on. So this is not monotonic, because it's flip-flopping back and forth between increasing and decreasing. On the other hand, looking at another sequence, suppose this sequence is 2n over 1 plus n. Now, in the first sequence, it was easy enough to show that it was not monotonic because we could list out a few terms and easily show that it's not. Showing that it is monotonic is a little bit tougher because we have to show that the trend holds for the entirety of the sequence. So what we're going to have to do here is that to show that it is monotonic, we must show that the nth term is always either smaller or larger or possibly the same as than the n plus 1th term. So what we would need to show here is we need to compare the nth term to the n plus 1th term. And the question is, what symbol should be in the middle? Should it be a less than or a greater than? We don't know yet. So let's do some algebra. We have 2 times n over 1 plus n. And then the other fraction, we can distribute the 2 in the numerator. And in the denominator, we can combine the like terms. Now, just for the sake of argument here, I'm going to put a single symbol in the middle and put a question mark over it to say we don't know if that's the right symbol yet. Well, to avoid confusion, maybe we'll do both and say, which one is it? We don't know yet. Now, to make this comparison, we're going to have to get a common denominator on both sides. So what we can do is multiply on the left side by 2 plus n, and multiply on the right side by 1 plus n. Now, something we would need to consider here is that when we multiply both sides of an inequality, if we multiply by a negative on each side, then that can reverse the inequality symbol. Now, we don't need to worry about that here because we multiplied top and bottom by the same thing, which is equal to positive 1. So we're essentially multiplying each side by positive 1. So whatever symbol would have been in the first statement is the same symbol that would be in this second statement. Of course, now they have the same denominator. So in order to compare which one is bigger, we need simply compare the numerators. Well, we can do this by distributing on the left side. That would give us 2n squared plus 4n. And foiling out on the right side, which would give us 2n squared plus 4n plus 2. And I think it should be pretty clear to see here that since both sides have 2n squared plus 4n, and then the right side has the plus 2 on it, that the right side is going to be bigger. So we can come back up here and say that it is the n plus 1 side the n plus 1 side that is bigger. What this means is that the subsequent term is larger than the previous term. This was the definition of non-decreasing. And therefore is monotonic. Now, the last concept that we need to talk about here is the idea of a sequence being bounded. There are three parts to this definition. First, a sequence, which we will simply call A sub n, is known as bounded above if there is some value which we will call big M, such that every term in the series, in the sequence, is smaller than or equal to that value. What this means is that every term of the sequence is smaller than this thing. No single term of the sequence ever gets above this value. In this case, M is known as the upper bound of the sequence. Likewise, a sequence can be bounded below if there exists some value, which we will call big N, such that all of the terms in the sequence are bigger than big N. In this case, big N is called a lower bound. Lastly, if all of the terms of the sequence are bound above and bounded below, then we simply call the sequence bounded. Examples of this would be once again, we'll take a look at this guy. This sequence is bounded. It is bounded above because no term ever gets larger than 4. And it is bounded below because no term ever gets smaller than 2. So this sequence would simply be called bounded. Some sequences are only bounded above or only bounded below. For example, a sequence such as 2n is bounded below because no term of the sequence ever goes smaller than 2. However, it is not bounded above. The importance of bounding, and again, a lot of what we are talking about in this lesson is going to become necessary when we start to talk about series, which is what the entire rest of this unit is about. But series are based on sequences, so many of the things we're talking about here will become relevant in later lessons in this unit. The last concept we need to talk about here is a theorem that says if a sequence is both bounded, which means from above and below, if it is bounded and monotonic, then it converges. If we wanted to break this down more specifically, we could say that if it is non-decreasing and bounded above, then it converges. If it is non-increasing and bounded below, then it converges. In a more general sense, if it is bounded on both sides and it is monotonic, either non-increasing or non-decreasing, then it must converge. The idea here is that a non-decreasing function a non-decreasing sequence means that each term of the sequence is bigger or at least no smaller than all the terms before it. Now, the definition of bounded means that there is some value at the bottom such that all of the terms of the sequence are bigger than it. And there is some value m such that all of the terms of the sequence are smaller than it. The idea then is if these terms are all getting bigger, or at least no smaller, then they are approaching some value. And assuming that m is the smallest possible upper bound, now there are many values that could bound a sequence. Coming back here, for example, we never said what the upper bound of this sequence was. I did say that the sequence is bounded above because all terms are less than or equal to 4. However, there are many values that could be considered an upper bound. The one that would make the most sense would be 4 itself, because that's the tightest we can get to it. We could say all the terms are less than or equal to 5, which is true. They are all less than or equal to 5. We could say they're all less than or equal to 10, which is true. They are all less than or equal to 10. But why would we go any bigger than we need to? 4 is a solid enough number to say all of the terms are smaller than or equal to 4. Same thing with bounding it from below. We could say it's bounded from below by 0 because all of the terms are bigger than or equal to 0, and that is true. But why would we go smaller than we need to? 2 is the smallest number that would work. 2 is definitely a value that they are bound from below by. So the idea here is that if we use m as the smallest possible upper bound, in that case, the terms of the sequence are approaching m, and that means the sequence converges. This is the very definition of convergence. On the other hand, a non-increasing sequence, which says that each new term is smaller than or at least no bigger than the term before it, that means that there is some term or some value up here such that all of the terms are smaller than it, and some term here such that, or some value here such that all the terms are larger than it. In this case, again, using the same idea that n is going to be the smallest or the largest possible lower bound, then the sequence a sub n approaches big N. And again, this is under the assumption that big N is going to be the largest possible lower bound. And in that case, this is equivalent to saying that the limit as n approaches infinity of a sub n is equal to big N. These are the very definitions of convergence.